Hello, and welcome to this lesson on mobile design principles. In this lesson, we will cover general designing concepts and implementation for mobile devices ranging from phones to tablets. We'll also take a look at the design language called material design, which is applicable to mobile and non-mobile application design. When designing applications for mobile, one of the most important considerations is to realize that you are most probably designing an application that is meant to be displayed on many different types of screens. These screens can vary in sizes, pixel densities, and even proportions of the device. In order to get the best results on all of these screens, we'll need to implement higher resolution images for higher resolution screens. And we'll also need to take into account screens of different proportions and change the layout of our application accordingly when needed. One of the major effects of the rise of the tablet market is the necessity for designing UI for multiple screens. On a phone where only one UI component may fit, we might be able to fit two or more of the same UI components on a tablet. Instead of keeping the UI consistent between phones and tablets, we can enhance our applications by having the UI change when presented on a tablet and take advantage of the additional space. The Android development system has several tools that can allow us to utilize these types of enhancements. Using adaptive design techniques, we can have the UI for our application adapt itself to the screen size it is displayed on, so that it will adjust to take advantage of more screen real estate. With the progression of Android operating system to incorporate tablet devices, the fragment component was created to represent a behavior or a portion of a user interface within a screen. This way, when a tablet application might consist of several portions of a user interface, these portions can then be reused separately or in conjunction in the phone version of the application, which can only display a portion of the UI components at once on its screen. These constructs also allow for separate UI flows for tablets and phones. When one UI component on a phone may navigate us to a new screen, the tablet version may simply change a currently present UI component instead of navigating to a completely new screen due to its additional screen real estate. Even within the same device, we may have to take into consideration multiple screens due to changes in the orientation of the device. One option is to keep the orientation of the application static and constant regardless of the device's orientation. If we want to allow our users the freedom to change the orientation of the device and have it affect the orientation of the application, then we need to consider how the application should be displayed on different orientations, like portrait and landscape. Android gives us the ability to completely change the layout and design of our screens of an application based on the orientation of the device. When designing layouts for your applications in Android, there are two sizing definitions that allow us to easily create flexible and adaptive UI. When setting the width or height of a view to match parent, it will ensure that it takes up the full size of its parent's view. When declaring the width or the height of a view to wrap content, it will set that size to a minimum size necessary in order to fit the content contained within the view on the screen. For example, in a list of items, like the ones displayed here, we can declare that each item should have a width that matches parent. That will ensure that rows take up the full width of the list. Then we can declare that the height of each row should wrap the content of the text within. That will ensure that each row will only take up as much height as it needs to display its text. In Android, the layout components allow us to design a visual structure for the user interface for a UI component or screen. These layouts can define preset rules and arrangements for their children views, which can be simple views like texts or buttons, or further nested layouts that define new constraints for their own children. In this graphic, we see a linear layout parent that defines rules for its children, which are two normal views, and another layout, in this case a relative layout, that can then define rules and arrangements for its three children, which are simple views. Two of the more popular and useful layouts are, as their class derivation is known, view groups, are the relative layout and the linear layout. The relative layout allows to arrange its children in a relative fashion according to other sibling children. For instance, you can define view A to be below view B, or view C to be to the right of view A. You can also align views to their siblings. For instance, declare that view D should align its left side with the left side of view B. In the image to the right, we have one large view with two views below, one aligned to the left of the top view and one aligned to the right of the top view. Linear layouts, on the other hand, organize their children in a linear order, one after another. They can be declared to set their children in a vertical column or a horizontal row, and will order them based on their children's declaration ordering. In the image to the right, we see a horizontal linear layout with one small view followed by a larger view to the right of it, followed by another smaller view to the right of that. In order to deal with the diverse set of screen sizes, screen resolutions, device languages, versions of Android, and other differentiating aspects between devices, Android allows for a powerful resource system. This system allows us to define specific resources for specific purposes based on qualifying that resource with a configuration qualifier. These qualifiers can mark resources to be used for specific screen sizes, screen densities, or even have different resources used for different orientation on the same device. In addition, resource qualifiers allow us to easily add multi-language support to our application. By using specific qualifiers, we can have the Android system use a different set of string constants depending on the locale definition of the device. Android has progressed significantly through the years from version to version, and in the case of a need for different UI or other components for a specific version of Android, we can utilize qualifiers to declare specific components for different versions of the Android operating system, identified in runtime on the device. As well, we can define qualifiers for things like UI modes or mobile country codes for the device to have the Android system use different assets for those cases. Here we have a few examples of how easy it is to use qualifiers to designate specific resources for specific configurations. In the first example, we want to define different graphics or drawable resources based on the screen resolution of the device. In Android, the screen resolution is usually defined in reference to DPI or dots per inch. Let's take the example of developing an application that has default drawables, which are graphical resources like PNG images, and higher resolution drawables, those for higher resolution devices. We can store our default drawables in our drawable folder in our resources directory, and store the higher resolution assets in the drawable-hdpi folder of our resources directory. In runtime, Android will use the resources based on the screen resolution configuration of the current device. When implementing multiple languages, we will use a similar naming convention to create different values folders. The values folder can contain resources from our string constants, arrays, colors, predefined dimensions, and styles and themes for the application. By adding a qualifier to the end of the values folder name, we can define values to be used for different locales. For instance, to implement multiple languages for our application, we can create a values folder, a values-es folder, and a values-fr folder in our resources directory. In the values folder, we would add a strings.xml file containing string constants for our default language, which in most cases would be English. In our values-es folder, we would add a strings.xml file containing string constants in Spanish. And in our values-fr folder, we would add a strings.xml file containing our string constants in French. Then when the application is run on a device with a Spanish locale or a French locale, it would use those string constants accordingly, or otherwise use the default string constants in our values/strings.xml file. Just that easily, we can define resources to be used for specific locales, screen types, or even orientations. Google recently announced a new visual language called Material Design. It was announced at Google I/O 2014 and included as the official design language for Android version 5.0 Lollipop, which was released later in 2014. Material Design offers a comprehensive guide for visual motion and interaction design across platforms and devices. In addition to its inclusion in Android Lollipop, the Polymer library brings Material Design to web applications as well. An important aspect of Material Design is that it is meant to be grounded in tactile reality, meaning that it is inspired by mimicking physical ink on physical pieces of paper. In order to achieve this imitation of the physical world, a Z property was added to views to represent their elevation. A major component of Material Design is offering the user visual feedback that provides meaning to the actions or transitions taking place. This can include intuitive transitions or responsive interactions with elements. These motions and effects should not be distracting, but should feel authentic and respect physical realities like mass and weight. Although Material Design was introduced in the Android version 5.0, the Android support library ActCompact version 21 offers backwards compatibility for some of the Material Design UI components and views. Material design also revisits color scheming to focus on a simpler and more refined color definition for applications. This enhancement is accomplished by using color palettes that predefine colors for elements like toolbars and action buttons. That concludes our lesson on mobile design principles. Join us next time when we learn how to utilize these design principles by declaring UI elements in XML files.